Thank you. All right, who said that? Collins?
Yes, sir.
All right. You did you just say record, Collins? I wasn't sure who that came from.
Oh,
It was Cameron.
yeah, Cameron.
Okay. All right, Collins. How do you feel about the derivatives of the first three?
Somewhat confident.
Okay, so derivative of sine x.
Cosine x.
Okay, derivative of cosine x.
Negative sine x.
Okay, how about tangent?
Secant squared x.
Yep, that's right. Okay, secant squared x. Now, the next three you may or may not have memorized. But remember, we have our formula sheets, right? And our formula sheets, it would probably be good to know where this information is on our formula sheets. If we scroll down to, what is it, reference page 5, that's where it talks about the derivatives. And you'll see here trig functions. Trig functions, right? And their derivatives here. So derivative of sine is cosine, derivative of cosine is negative sine. So the other three, derivative cosecant is here, derivative of secant, and derivative of cotangent, right? So these are all here. You don't have to memorize them. Our goal today is to actually see where these come from. These are your inverse trig functions, and those are their derivatives. There's 6 of them. So that's what we're going to try and figure out, is where in the heck do these derivatives come from, all right? So back to this. We have these, we know these, I'm just going to put checks here, we know what they are. Okay, and now what we're going to do is we're going to say, all right, for each inverse trig function, let's determine what the derivatives are. So for this, what's the derivative, and so on and so forth for each of the inverse trig functions. That's our goal, and then we'll see how we can use that, once we know what they are, how we can use that to continue to differentiate things using chain rule, product rule, quotient rule, implicit differentiation, all the things we did in Cal 1. So all we're really doing today is adding a new group of 6 functions and their derivatives. All right, so before we actually start looking at what the derivatives are, let's remind ourselves of what an inverse trig function is. So without getting into too much detail, we know that when you look at a trig function, our standard 6 trig functions, sine, cosine, tangent, cosecant, secant, cotangent, all these different trig functions, none of them are one-to-one functions. Meaning, in order to be one-to-one means that you have to pass both the vertical line test and the horizontal line test simultaneously, and none of these functions do. So it's impossible to have an inverse when your function is not one-to-one. So what we do is in pre-cal, we say, all right, well, to make an inverse possible, we can restrict the domain. So if we look just at the sine function, there's the sine curve. If we just restrict ourselves to this section right here in blue, I hope that showed up on your end okay. I'll take out the whole thing. If we restrict ourselves just to that little piece of the sine function, it is one-to-one. It passes both the vertical and horizontal line test. And in that little segment, we achieve every value within the range, from -1 all the way to +1. So within that little window, we can define an inverse trig function. And we do. We call it arc sine, or sometimes we use this notation, sometimes we use this notation. Either way, we have this definition where we have a restriction, a domain restriction on the original sine function between pi/2 and -pi/2, and that's the little window we're looking at. And then from there on, you have the idea of the inverse. So just more of a basic understanding of what inverses do. You know, if we have a function here, a function that goes from its domain, it takes things in, right? This is your input. It's going to take these things in, it's going to spit something out over here, which is called a range. All right, and then an inverse function is the function that basically undoes that. So in terms of, like, let's take one specific example. If we have like the sine function, So if we make this function f here, let's make it the sine function. I'll just put sine x. Then it's going to take in numbers, right? You plug a number into the sine function, it's going to spit out a number. Now the number that you plug in is actually an angle, isn't it? I'm going to label it theta. Theta is still a number, but it's an angle when you plug angles into trig functions, and it spits a number out on this side. The inverse function, okay, this inverse function, arc sine of x, takes numbers and sends them back to angles, right? That's the whole idea. So I just want to make sure we have this visual understanding of how the trig function and inverse work. They work like a loop, and that angles go to numbers and then numbers go back to angles. Okay, we can do that. We can do this sort of domain restriction for all the other 6 or the other 5 trig functions, right? For cosine, of course, it's not 1-to-1, so we restrict its domain. So does anyone remember the domain restriction for cosine if you want to define its inverse?
Is it pi over 2?
That's sine. Sine goes from negative pi over 2 to pi over 2.
Is it 0 to pi?
0 to pi.
0 to pi.
That's our domain restriction for cosine, if you want to define its inverse. And then same with tangent. There's a domain restriction there. It's between negative pi over 2 and pi over 2. And each one.
I have a question real
Yes.
quick. So are we supposed to remember all these domain ranges? Because I know I remember them, but I'm not sure.
I think that you should be comfortable with the idea of sine and cosine, the first 3. You should know that in order to define sine's inverse, you have to be between negative pi over 2 and pi over 2. And for cosine, you have to be between 0 and pi. And for tangent, you have to be between negative pi over 2 and pi over 2. Those, it'll make your life a lot easier if you know and understand those. And we're going to do a problem here in just a minute, and you'll see why it's important. Now, as a reference, I believe, again, that the formulas, here we go, right here. So this is on the reference page for reference page 3. It talks about the arc sine function, and then it says that the restriction here is negative pi over 2 to pi over 2. Here's the arc cosine, it's between 0 and pi. And then the arc tangent is between negative pi over 2 and pi over 2. And you have to be a little careful here because arc sine and arc tangent are almost the same, except that with arc tangent, you do not include the endpoints. Like you do not include negative pi over 2 and pi over 2. They're not part of the domain. Does that answer your question? Just those first 3, at least? Okay, so let's do a problem here. This will be interesting to see how your brain works when it comes to trig functions and evaluating trig functions. So I'm going to take this first example here, and you know what? I'm going to switch it up a little bit because I've done these problems so many times. I'm going to just switch it up. I'm going to do what is cosine inverse or arc cosine of -1. Okay. So let's see if we can't, well, let's make sure we understand how you should be looking at this, all right? Like I said, everyone's gonna have kind of a different sort of idea here, but here's what I'm gonna do to kind of help. I'm gonna say here that this is equal to theta. And the reason I'm saying it's equal to theta is because I know that the output of an inverse trig function should be an angle, right? We have the input here, which is a number. And once I send it through the cosine inverse function, it should spit out an angle. So I'm going to call it theta, right? So really what this question is asking me is it's saying, look, when you take cosine of some angle, the answer is -1. Can you tell me the angle? Okay, so saying what's arc cosine of -1 really means cosine of what angle is -1. So I'm not going to call on the next person right now. I'm going to take a volunteer for this one to tell me, someone who wants to tell me. What's that?
Is it pi?
It's pi. Now, why do you know it's pi? I'm just trying to.
Because like you said, when you're on your unit circle, whenever you're talking about cosine and you're trying to find the angle theta and you want it to equal -1, the only place on the unit circle that it hits it is on the very left side, because you're talking about cosine, you're talking about your x value. So you
Okay.
know, yeah.
Perfect, James. That's exactly what I was hoping you would say. So this is where it's going to differ from student to student, how they learn things, how comfortable they are with the unit circle. When this question is asking at what angle, so it's saying, look, at what angle theta is cosine -1. So you have to understand that on the unit circle, cosine refers to the x coordinate on the unit circle and sine refers to the y coordinate. Again, x is always cosine of theta and y is always sine of theta. Now, there's one other thing that James had to know in order to answer that question. He actually had to know some of the common points around the unit circle. So James knew that the point here is -1, 0. So he already knew that the only place on the unit circle where the x coordinate, which is what corresponds to cosine, is -1, happens at that point. And then James knew that that angle is pi. So the answer is pi. Good. Any questions on that? If you're not comfortable with the common angles and the common values of the trig functions around that circle, this can become very difficult, all right? If you're constantly having to look over at a unit circle and, you know, because like on a test, you don't get a unit circle. So the sooner you understand that unit circle, I think the better off you are. Let's do another one. I'm gonna make this one up. How about arc sine of a half? Okay, so this question, let's go to Maria. Maria, are you there?
Yes.
Okay, Maria. So Maria, just like I did up here when we had cosine inverse of -1, I converted that into an equation, right?
Mhm.
What equation does this turn into then?
Would it be sine theta equals pi/6?
Well, I think you're already giving me the answer. I'm just saying, when we are asking what is arc sine of 1/2, you're really saying sine of what angle, sine of theta, when is that a half, right? That's the question we're asking. And then you gave me the answer already, right?
Okay.
You're telling me that it's pi/6. And again, is that coming off the unit circle for you?
Yes.
Okay, and do you have that unit circle kind of like hardwired kind of, or are you having to reference it?
100%, but like at least the top part I know for sure.
Yeah, I think it's probably a really good idea for everyone to have at least the first quadrant memorized. You know, you should know that at pi/4 or 45 degrees, you should know that the coordinates are √2/2, √2/2.
Mhm.
You should know that at 30 degrees or pi/6, it's √3/2, 1/2. And then you should know that at 60 degrees or pi/3, it is 1/2 √3/2. If you've got that first quadrant memorized, usually all the other quadrants are some sort of reflection, and all that happens is the x and y values, positive, negative values change. Okay, so you realize there, Maria, that we were talking about sine, and when we talk about sine, we're talking about the y coordinate. So you were just asking yourself, where is the y coordinate 1/2? And you said right here, and then you said that angle is pi/6.
Yes.
Right?
Yes.
Okay, now let me ask you, Maria. On the other side in the second quadrant, over here, there's a point and it's -√3/2, 1/2. That's this point right here. Why didn't you give me that angle? Because this angle right here, which is 5 pi/6, why didn't you give me that answer? Because I see a y coordinate there, 1/2 also.
Mm, honestly, I just thought of which one would be the first one, which was the first quadrant, and that's just what first came to mind to me. I normally don't think of the second quadrant, to be honest.
Okay, good. I mean, that's what I want to know. I want to know, honestly, like how you're looking at this and perceiving it.
Sine,
Yeah.
sine can only be, the inverse sine can only be on the interval from -π/2 to π/2.
Yeah, so James pointed out, remember, we have a domain restriction, and that domain restriction is critically important because if you can only be between -π/2 and π/2, π/2 is straight up, right? -π/2 is straight down. So really, in reality, if we're going to be talking about the arc sine function, if we're going to be even able to do anything with it, we are only allowed to be looking at angles between -π/2 and π/2. Everything else on the left-hand side of the unit circle is off limits when we're using an inverse sine function. So that is why 5π/6 cannot be an answer. It can only be π/6. And that we only do that when we're talking about arc sine. If we're talking about arc cosine, where are we restricted? So I'm just going to do it over here. If we're
Arc
talking about arc
cosine,
cosine,
0 to pi.
0 to pi. So we throw out the bottom two quadrants. You can only be between 0 and 180 degrees. Okay, that's for the inverse cosine. Okay, let's do one more. How about arc sine of negative, let's do -√3/2. So this is really asking us the question, sine of some angle, which we don't know yet, is -√3/2. And because it's sine, that means I'm going to go to my unit circle and I'm going to look at the y coordinate. And I'm going to try and figure out where on the unit circle my y coordinate is -√3/2. And I can only be looking in the first and fourth quadrants. I'm not allowed to look anywhere else. So I'm going to do this. I'm not looking here. I'm hoping that one of my common angles has a y coordinate of -√3/2. So let's see here. Christian, you're up.
5π/3.
5π/3. Let's see. So
Since you're limiting your
hold on, James. I got you. I know where you're going, James. Hold on for a second.
I'm sorry.
No, that's okay. So 5π/3, right? I think we all agree that 5π/3 is that angle. But there's a problem with 5π/3 because remember, we have a domain restriction. So you cannot go through the second and third quadrants to get to this angle because now you're bigger, right? So Christian, what are we going to have to do? Do you want to do Christian or CJ? What do you like? I can change.
I like CJ. I'm cool with CJ. I prefer
CJ,
that.
I'm going to change you over here. That way I can call you CJ from here on out.
So it's -π/3, correct?
There you go. Yep, there you go. So
I forgot about
we're just
that.
we're gonna move backwards, right? We're gonna just say,
Yeah.
okay, we're gonna go backwards instead. So -π/3. James, that's what you were gonna say, yes?
Yes, sir. Yeah.
Yeah, I'm still refreshing on this.
Yep. So I gave you that example exactly because that's a common mistake, is to grab the angle going all the way around, but you can't. You got to go backwards. Okay, so that's just kind of to get our brains going again with inverse trig functions and how you have to be a little bit careful when you evaluate them. Let's move on. I already said that every inverse trig function has its own domain restriction. The book has them. Our formula sheets have them. We are just going to move on, okay? We also have this thing called the cancellation property. The cancellation property is very nice. It just says that if you take a trig function and you compose it with its inverse, they basically wipe each other out. Now, there are some domain issues we have to be concerned about there, but in general, not in general, well, yeah, in general, as long as the domains as long as the domain restrictions are satisfied, the idea here is that if I start with some value of x, I send it through, let's say, sine, get something out here, and then send that value back through the inverse trig function, that it's going to go right back to x. So if I do arc sine of x, if I do that composition, my answer should just be x. And that works both directions. If you do the sine of arc sine of x, you should get x. So this is a very, very, it's really what makes inverse functions. When you compose them, you get whatever went in originally. So it's almost like an identity. And that works for all 6 inverse trig functions, so long as domain restrictions are met. Okay, moving on. Finally, we get to do a little calculus. So now we want to talk about the derivatives of these, because really, we studied these already in pre-cal. So what we want to know now is, can we find the slope of the tangent line of these curves, the instantaneous rates of change? Is that possible? And to do this, we're actually going to need to be able to do 2 things. We're going to need to be able to do something using what are called reference triangles, and then we're going to need to be able to do implicit differentiation. All right, so to be able to show you what the derivative of an inverse trig function is, we're going to have to employ these 2 techniques. Now, once I show you what the derivatives are, you don't have to ever prove them again. Okay, so we're about to show where the formulas come from. But once you have them, you just look at your formula sheet when you need them. The reason I'm showing it to you, though, the reason I'm showing you this step is because these 2 techniques that we're using right here, we're actually going to use these later for problems. So this is your first opportunity to kind of reacquaint yourself with the idea of a reference triangle and reacquaint yourself with the idea of implicit differentiation. So here we go. Let's just start out with the first one. I'm going to say, let's say we have a function. I'm going to call it y equals arc sine of x. And then the question here for us is to find y prime. And remember that y prime really means dy dx. Right, so we're treating x like the independent variable, and we're saying that y depends on x. So when we talk about y prime, we are talking about dy dx. Right, so right now we can't do anything, right? I mean, we could differentiate both sides of the equation, but so like I could differentiate the left side. Derivative of y with respect to x would be dy dx. But then I would need to know what's the derivative of that, right? But I don't know that. That's the whole point. We're trying to figure out what the derivative of that is. So there's nowhere we can go with just differentiation right now. So here's what I'm gonna do. I'm first gonna use the cancellation property. So I'm going to take this and I'm going to take sine of the left side. And then I'm going to take sine of the right side. Now, the reason I'm doing that is because the cancellation property on the right-hand side should leave me with what on the right?
X.
Just x, right? And then on the left-hand side, we have, well, sine y. Okay, great. Now, at this point, I can differentiate both sides of the equation. I can do that. And the good news is now I no longer have an inverse trig function there, which I don't know anything about the derivative of an inverse trig function. But I do know what the derivative of sine is. So at this step, I'm going to take the derivative with respect to x on the left side of the equation and the derivative with respect to x on the right side of the equation. All right, let's get someone involved here. Sergio. Where's Sergio out? Is he here?
Yes.
There you are, Sergio. Okay, Sergio, let's start with the easier part of this, the right side of that equation. The derivative of x is?
0.
That's derivative of constant.
Oh, sorry, I'm my bad. 1.
1, okay. Now, on the left-hand side, you have to take derivative of sine of y with respect to x. So this is actually chain rule. You start with the outer layer, right, Sergio? You
Yes.
say, what's the derivative of sine of y? What would that be?
Sine of y will be cosine.
Cos y, okay. But you're not done, right? You have to multiply this times the derivative of what's in here, right? And the derivative of y is not 1. The derivative of y is?
One.
The derivative of y. I mean, that's what it is, right? The derivative of y is the derivative of y. We don't know what that is,
We
but
don't know
isn't
yet.
that what we're
Y
looking for?
prime.
Yeah.
Isn't that what we're looking for, right?
Mhm.
So that's where our y prime comes from. And there we're done with the derivative on the left. We've already done the derivative on the right. And the good news is that what we're trying to find in this problem has just appeared, right? Y prime is now here. So let's isolate that y prime by itself. So to isolate the y prime, all I'm going to do is divide both sides by cosine y. And that's the derivative. That is the derivative of arc sine of x. Now there's a problem with that derivative. The problem is that our original function was a function of x, right? And we're saying that in order to know what the derivative is, you need to know what 1 over cosine of y is. Like x is no longer here, right? Y'all see that? Like x isn't here. So what we want to do is see if we can't get our answer here to have x in it instead of y. So to do that, what we're going to do is create this reference triangle. So I'm going to draw a triangle over on the right-hand side. It's going to be a right triangle. And we know a lot of things about right triangles, right? We know Pythagorean identity, a squared plus b squared is c squared. We know that if someone gives us an angle, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. We know all the different relationships, right? But what I'm going to do is I'm going to go back to this line right here. Before I took the derivative, right? Before I took the derivative, I had this statement, sine of y equals x, right? Didn't we have that statement? So if I look at that, do you agree that I could, if I label my triangle this way, if I call that angle in the right triangle y, then that's kind of like the angle here, sine y. If that has to be equal to x, I could rewrite x as x over 1. And we know that sine is always the opposite over the hypotenuse, right? So if I label this opposite side x and the hypotenuse 1, then that triangle is a visual representation of that equation, isn't it?
Yes,
Does
sir.
anyone have a question on that?
I lost you.
Okay, so I started out with this equation here. And what I said is, I'm going to draw a triangle that is going to visually represent what that equation is really saying. That, because this equation is saying sine of some angle y is x, right? And my triangle, if I ask you right now to look at this triangle and I ask you what's sine of y, what would you tell me?
Opposite over hypotenuse.
Which would be?
X over 1.
Which is just?
Yeah. X.
So you're telling me that sine of y would be x, right? That's what you're telling me? See, but that's where we started. So what we're doing is we're taking that equation and we're like reverse engineering it and creating the triangle from the equation. Make sense?
So I guess
Yes,
a good way of thinking about it would be that y is like theta in this case.
Exactly. Y is the theta. Y is the angle, right? Y is the angle. And then this side over here is always going to be, well, depending on the trig function. In this case, it's sine. So the x here is going to be your opposite over hypotenuse. But had that said cosine of y, then we'd be looking at adjacent over hypotenuse. Had that said tangent of y, then it would be opposite over adjacent. Is that better? We good? Okay, now what is the benefit to having that triangle? Why am I going through all this?
So you can use a Pythagorean identity theorem.
Okay, so I could solve for this side, couldn't I? If I have two sides of a right triangle, I could always solve for the third, right? Why would I want to though? I mean, like what, again, where am I going?
Because we need that value for the cosine y that we got earlier.
Yeah. So
we want to make it in relation to x.
Yeah, good. We have this cosine of y, right? That's what we have over here. And now I could ask you right now, looking at this triangle, what's cosine of y? And everyone would say adjacent over hypotenuse, right? Mm-hmm. Now you don't have the adjacent side yet, but we can get the adjacent side. But to do that, we could just do Pythagorean. So I'm going to label this adjacent side A. And let's just all agree that a squared plus x squared is 1. That's the Pythagorean identity. And let's solve for a. So a squared equals 1 minus x squared. And then you get a is equal to the square root of 1 minus x squared. So your adjacent side is the square root of 1 minus x squared. So now from this triangle, if we say what's cosine of y, it's going to be adjacent over hypotenuse, which is just square root of 1 minus x squared. Now I'm going to take that answer and I'm going to come back over here and put that in. So y prime is equal to 1 over the square root of 1 minus x squared. There it is. And if you go back and look at your formula sheets, well, we'll go back and look right now. There it is. I hope y'all can see that. Oops, I'm hyperbolic. I'm looking at the wrong ones. Here we go. The derivative of the inverse sine function, arc sine of x, is 1 over the square root of 1 minus x squared. So that's that formula. We just derived it, right? Any questions?
Sir, when you take the square root of both sides, isn't it plus minus?
I was hoping you would ask. I was really hoping someone would actually challenge me a little bit on that, because I did. I kind of slid that by you, didn't I? So I don't know. Maybe you can tell me why I didn't include the minus.
Because we have the domain restriction.
Well, in some sense, you could talk about the domain restriction. Think of it more from just a geometric perspective. Like, what is A here?
A is positive.
It's the length of a side of a triangle, right?
The length. Yeah.
So we couldn't really get a negative here.
Yeah.
It wouldn't make sense.
It depends on what quadrant you're in, though, right?
Well, algebraically, you've got plus or minus. Like if we had no pictures to this, we didn't know any of this had anything to do with trig functions or inverse trig functions, then we would be like, yeah, there's two answers, okay? But because we're dealing with the inverse sine here, then we know that we're actually in one of these two quadrants, right? Mm-hmm. And so if you draw your right triangle like this, or you draw your right triangle like this, doesn't matter which way you draw it, notice that the A part, the adjacent part, is going to be positive. Right. That's a little deeper understanding than I think we absolutely have to have, but that is mathematically, that's why it doesn't, that's why we take the positive. Good question. Okay. Thank you. Okay. All right. So we have derived the derivative for one of them, right? For one of the 6.
Yep.
Now I'm not going to derive all of them. I'm going to do one more, and I'm going to do, I think, well, I'm going to do it, but I'm going to really ask you to help help me. Hold on. TV will turn on. Getting a little alert here. That's okay. Arctangent. Let's do arctangent. All right. Joseph. Where's Joseph at? There you go. Okay, Joseph. So using the same sort of template, the same sort of idea, Joseph, from the problem we just did, if we want to find the derivative of this, what would our first step be? I know we know nothing about the inverse tangent derivative, so oh, the TV just turned off. Shit.
We have to do it with respect to x, right? So we're gonna have to do the dy dx on each side.
Okay, we can't do that yet because we don't know what the derivative of arctangent is. So on the previous one, I did something first to get rid of the inverse function. What did I do? You see it there? Did you write it down?
Yeah, I have it written down, but I'm just a little bit confused.
Okay.
Cancellation.
Do we find the tangent of y?
Trying to
from
get
the
the
tangent?
arctan out. So we would have to take tangent on both sides of this equation. Now, for those of you who are really on top of things here, when I say I'm taking tangent of both sides of the equation, technically I am not taking tangent of both sides of the equation. Like mathematically, I am just using the fact that the functions are one-to-one, and this is a property of one-to-one functions. So it looks like I'm doing algebra, but it's actually a property. Anyone who might like know that already, just please know that I have an asterisk next to this when I say that. Like I am aware that that's an actual property, but students just do fine when I say take tangent on both sides. So tangent of y equals x, right? So the first step is to get rid of the inverse trig function by using the cancellation property, bringing in the trig function on both sides. Then at this point, you can differentiate, okay? Is there a question?
I'm hearing a hello, but it's really faint.
Yeah, it's all right. Okay, Joseph, is that okay?
Yeah.
Okay. All right, let's continue with Benjamin. So Benjamin, what's going to happen here? Ben or Benjamin? What do you? I see Ben on the screen.
Either one.
I'll put Ben on here. That way it's consistent.
All
right,
cool.
Ben, I'm asking now for you to differentiate both sides of this equation with respect to x.
Mm-hmm.
So what do you got?
It'd be 1 on the x side right here.
Okay, so on the right side we got 1. Left side?
Left side, you just take the just be the same. Wouldn't it just be the same? Because
what's the derivative of tangent of y?
Hold on. I forgot it.
Okay, so that's one of the three. We have to have hardwired secant squared y. But you're not done. You're not done because it's
then you gotta do the inside, yeah.
Yeah, and the derivative of y
is
dx. dy
Okay.
dx. Or I'm just going to put y prime, and we all understand that's dy dx.
Yeah.
And then we do the same thing we just did a second ago. We solve for y prime, right? So y prime is 1 over secant squared y. So I divide both sides by secant squared y. What is secant though? Isn't secant the reciprocal of something? Secant's really 1 over cosine, right?
Yeah. Cosine.
So I could actually rewrite this as cosine squared y. What I'm doing there is I'm rewriting this as 1 over secant y that quantity squared. Those are the same, but then I'm rewriting secant y as cosine y, and then I'm just squaring it. So the derivative of the arctangent function is cosine squared y, and we have the same problem we had before, where I don't want my answer in terms of y, I want it in terms of x. So now comes the reference triangle. And this is always the part that can get people a little confused. So let's see where Alejandro is with this. So do we have Alejandro here? I see Alejandro there. Are you present? Maybe not. Okay.
Maybe
How about
not.
Kelsey? There's Kelsey. Kelsey, are you following this okay?
I have been, but
Okay.
right now I'm not sure.
Until I called on you, right?
Yeah.
Okay, so we need to create this triangle. We need to label the sides of the triangle, and it's going to come from an equation somewhere on the left-hand side. Do you know which equation I'm going to use?
Y equals X.
Y equals which one? I didn't hear the whole thing you said. Did you say tangent y equals x?
Yes.
Okay, sorry, all I heard was y equals x. Tangent y equals x, perfect. Okay, now the angle is y, so I'm gonna put y here. And then it would be helpful if we looked at x as being a ratio, like x over 1. So Kelsey, tangent on a right triangle, tangent is which side over which side?
Opposite over adjacent.
Okay, so I should label the opposite side here what?
X.
Mm-hmm. And the adjacent then would be?
1.
1. Okay. Now, what are we interested in here? Like, in order to answer the original question, we actually need to know what cosine of y is, right? That's what we want. Y'all see it here in blue? We want to know what cosine of y is. So we need to know what adjacent over hypotenuse is off this triangle. Do we have the hypotenuse?
No, but
Not directly. Not directly, right? But we have it indirectly. So we can solve for it. Now, I'm not going to go through the actual solving of it. I'm just going to put it out here. I'm going to expect everyone in here can get this. That's a plus sign between them. Sorry about that. So you just do the a squared plus b squared equals c squared and solve for c, and you should get that. So cosine of y, let's write it down here. Kelsey, you're off the hook. Cosine of y. Amber, is Amber around?
Yes.
Okay, Amber, what's cosine of y then for us?
Is it just the square root 1 plus x over 2 over 1?
Other way around. So cosine is adjacent over hypotenuse, right? So it's 1 over, there you go. Okay. And then when we come back over here to the left side, we want to take that answer and square it, don't we?
Yes.
We want to take this and we want to square it. And when we square that, you're going to get rid of the square root, right? You're just going to have 1 over 1 plus x squared. And that's it. So if you look at your formula sheet, again, that will be the derivative that you will see there for arctangent right here. There it is. And I'm going to put I'm going to put a star next. No, I'm going to put 2, no, 3, 4. I'm put 5 stars next to that formula because you're going to become very intimately connected to that formula. We're going to use a lot. So the sooner you memorize that, the better. The other derivatives, the other ones for inverse trig functions, they do come up, but that formula comes up so much that you don't want to have to be looking it up. Like you just want to have it up here, okay? So derivative, the derivative of arctangent of x is 1 over 1 plus x squared. That's it.
Can you tell us why that always comes up more than the other two?
It has to. Oh yeah, I can tell you. It has to do with the fact that. Let me get to a blank page here. Has to do with the fact that we will be doing a lot of things that involve quadratic functions later, and we know that anytime you have a quadratic function, let's just say like let me do it this way. When you have like, well, let's just look at a quadratic expression, that we can always complete the square on that expression. So if I complete the square on this expression, let me make this so it works out a little bit nicer. I'm put a 9 on the end of that. If I complete the square on that, and let's not get into the details of completing the square. If you don't know how to do it, you don't remember, that's fine. Don't worry about it right now. You will have to worry about it, just not right this second. So we take this number in the middle, we take half of it, which is 2, we square that, and then we do some stuff with it. And at the end of it all, you wind up getting like this, if you complete the square. And if you kind of squint your eyes, this looks like something squared plus 5, right? And it's hard to see it now.
U substitution.
Yeah, it's like a U substitution, but there's a way to make that kind of looks like U squared plus 1. I mean, the 5's a 5, but it's kind of like a U squared plus 1. And so what we're going to learn later is that anytime you have a quadratic in the denominator, like let's say we're trying to find the antiderivative of something. And let's say we have a quadratic in the denominator. We can always complete the square on this and make it look something like this. And once it looks like that, it's really close to being the derivative of arctangent. Does that make sense?
Yes, sir.
Okay, so it has to do with the fact that later on we're going to be doing antiderivatives of quadratics when they appear in the denominators, and it's very natural that a quadratic can complete the square into something that looks like something squared plus something, which is exactly what the arctangent function's derivative looks like. So yeah, we'll see it more, but I think that's good enough to at least explain kind of why.
Okay, cool. Thank you.
Yep.
I thought it was because when we start doing integrations, that comes up a lot when it goes backwards.
Yeah, it does. It does, because that's exactly what I'm saying. When we do antiderivatives, anytime we have quadratics in the denominator.
Okay.
Yeah, because look at this formula. If you look at that right there, this is a quadratic in the denominator, right? Isn't it?
Mm-hmm.
Now, it looks like it's missing an x term, right? But we know that if we complete the square and do a substitution, we can basically make it look like this. And that'll be good enough for what we're trying to do.
Okay.
Yeah. All right, moving along. There are 4 others, right? 4 other derivatives of the inverse trig functions. Like I just said, you should know that they're on your formula sheet. You should have that one that I told you memorized. Now let's try and see how we do with actually implementing those formulas in just everyday differentiation, things that we've, chain rule, product rule, quotient rule, things like that. So I should have done this before. I was just here a second ago. I'm going to grab all these. That way we can use them here. Okay. So for this example, what we're going to do is we're given this function y equals the square root of natural log of arctangent. Oh shit, I'm sorry. Oh, pardon my language. I meant to do the one up here. Sorry, I got ahead of myself. Arc sine of the square root of 1 minus x squared. All right, so we want to find the derivative of this. So the only thing that's really new here is that we have the inverse sign here, right? So this is going to require what rule? Like what differentiation rule is going to be required in order to do this?
Product rule.
So do we have a product? Do we have something times something?
This is chain rule. My
This
bad.
is chain rule. Yeah, this is chain rule. We have arc sine of, right? So if I were to like try to verbally say this, this is arc sine of the square root of 1 minus x squared. So we actually have like 3 layers to this onion, don't we? We have the arc sines on the outside, then we have inside that we have the square root, and then inside that we have a little quadratic. So we have to apply the chain rule. And I told all of you last time, you know, the Cal 1, you've got to be pretty good with the Cal 1 to have any success in Cal 2. I'm going to differentiate this right now using chain rule. I'm going to do it all pretty much mentally. So if you're doing chain rule and you're still at a point on your chain rule where you have to write it down, and like, because when you're learning chain rule in Cal 1, a lot of times you're told to like rewrite it like f of g of h of x, and then you use all these little formulas and stuff, which is fine when you're learning it. But you really want to be comfortable to the point that you can do this without that. If you're not there, then that's something you can practice, work on. Meet me in office hours. I can try and help you shorten that process for you. Okay, let me do this first one. So the derivative. So the first thing I'm looking at is the arc sine. And I'm just saying to myself, what is the derivative of arc sine of some crap? Okay, so the crap is the x. Okay, I kind of highlighted it there in like this reddish purplish thing. The derivative of arc sine of some crap or some junk is just going to be 1 over the square root of 1 minus, now not x, right? It's everything that was in the argument of that trig function, which should be the square root of 1 minus x squared, but all of that has to be squared. So do you all see that that is just this formula here, replacing x with the argument that was inside of the inverse trig function? The argument being everything in blue and green. So that's my blue, and that's my green. They're all in there. That's like the x.
So this is also done in Cal 1, I think.
Oh yeah, this is Cal 1. The only difference between what we're doing right now and in Cal 1 is you have a new type of function you can differentiate, right? The arc sine. Like now that we have them, let's just practice differentiation real quick. Just make sure we're comfortable with it. That's all we're doing. So I'm going to do times because this is chain rule. And now I'm done with the arc sine. I've got to move to the next layer of the onion, which is the square root part. And what is the derivative of the square root of something?
Again, chain rule. 1/2 plus whatever's underneath the radical to the negative 1/2.
Good. So I want to have a brief discussion about this underneath here. Back in Cal 1, when you're given the square root of x and you're asked to take the derivative of it, you can rewrite that as x to the 1/2, take the derivative, and then you use the power rule. The 1/2 comes out, x, and then you subtract 1 from 1/2 and you get a negative 1/2 up there. That is the correct answer, all right? But you can also rewrite that as 1 over 2 square roots of x. And all that is taking this negative exponent here, dropping that x down to the denominator and then rewriting it in radical notation. Do y'all agree with that? Every single time I take a derivative of root x in this class, I will always go straight to that. I'm not going to use this version of it. I'm just telling you that. So I'm going to go right to this. So I'm going to say in this part, the derivative, for me, the derivative of this thing is going to be 1 over 2 square roots of 1 minus x squared. So the only thing that's in there here is, this is the green part. That took the place of the x in the formula, right? Still not done. Right? There's still more to do. We now have to take the derivative of the next part that's inside, which is the quadratic part. And that's a nice one because you can just do the derivative of each one of those separately, and you should get negative 2x. And now we're done with the actual chain rule. Are there any questions on that?
Sure. Are you ever gonna have us combine it? Like,
yeah, I'm gonna clean it up a little bit.
okay.
Not too much, but I'm gonna clean it up a little bit. So one thing I'm gonna do is on this one, I'm gonna write this as 1 minus x squared. I'm gonna use the fact that this squared right here is gonna kill off that square root. And so when you kill that off, you're gonna be left with just the 1 minus x squared underneath the radical. And then over here, I'm going to kill off these 2's. I'm gonna put a negative x on top, and on the bottom, I'm gonna put the square root of 1 minus x squared. And I think one more thing I'll do is I'll distribute the negative through this parentheses. So that'll give me 1 over square root of, what is that? What's my new denominator there?
Negative x squared.
Plus minus?
No, positive x squared.
Positive.
X squared.
Yeah, the ones cancel.
Negative.
You have an x squared there, right?
Yes.
And then you have times negative x over square root of 1 minus x squared. Can we do anything else?
We can distribute the denominator since they're both under the square root.
Okay, you mean like I could just put those together and pass the x squared through?
Yep.
I could do that. I like that.
So it's just gonna be negative x over 1, under root 1, I think.
Yeah, let me do that, but I want to just make sure real quick. Be careful on this. We have this denominator, don't we? Right here. We have this. Be careful, that is not equal to x. A lot of times people will simplify that to be x, but it's actually the absolute value of x. So just be careful that you can't turn that into x. And the danger would be if you turn this into x, then you may be tempted to cancel these. And that's a no-go. So this is that. Yeah, so what's being suggested here is we could just do like maybe one more step where we do this. We put the x squared in here. Like we put these two radicals together because they're being multiplied. So we just put both of the radicands, the thing underneath the roots, together with multiplication. And you could even distribute that through, but I'm just saying we're done. I think I'm happy with that.
Sir, I don't want to stray too far from the lecture, but why does radical x squared equal like absolute value of x?
Well, just give me a value of x.
2.
Okay, give me a value of 2. Okay, so I plug 2. Just imagine I plug 2 into there. Become 2 squared, right? Square root of that, which is
2.
Square root of 4, which is 2, right?
Yeah.
Okay, now how about negative 2? Okay, let's say we plug in negative 2. And that would be squared, right? And then square root, what would that be? Square root of
negative 4,
which is 2, right?
2. Yeah.
So what happened on this first one is that you plugged in 2 and what did it spit out? 2. And on the second one, you plugged in -2 and what did it spit out? 2, right?
Yeah.
Isn't that the same as the absolute value of that? Like if I ask you, what's the absolute value of 2, you're going to say 2. But if I say, you know, what's the absolute value of -2, you're going to say 2, right? What did not happen is that you did not plug -2 in here. We did not plug in -2 and get -2. So it's not true that this is equal to x, because if we try to plug -2 in, it's not equal to -2. I hope that makes sense.
Yeah, that makes sense. Thank you.
Okay. Good question. Questions like that, don't feel like that's straying from the lecture, okay? That's definitely on point enough. Straying from the lecture would be asking me what I think of the NBA boycott. Now that would be straying from the lecture. We're not going there, okay? We're not going anywhere political in here, right? I want to keep my job. All right. Oh. Especially since I'm recording, right? We talk math. That's what we talk. I can't even imagine being like a political science professor right now.
Yeah.
And what kind of fine line do you have to walk? My goodness. All right. Stick to the math. Stick to the math. Next problem. Got quiet in here. All right, there we go. So, you know, this is stuff we've done in Cal 1. It's just now we've got some inverse trig stuff in here. So we start, this is another chain rule problem. So we're going to start on the outside. We've got the square root's going to happen, and then after the square root, we've got a natural log, and then after we've got the natural log, we've got the arctan. So we're just going to work from the outside in. And I want to get through everyone today. So how about James? James, you've already answered, but you want to go? You want to go ahead? Up to you.
Want me to give you the derivative of that?
Yeah, go ahead. Or at least the first part of it.
Taking your square root, the first part.
Mm-hmm.
Sorry, I was talking to somebody. I'm kind of lost.
No, it's all right. Don't worry about it. I'll kind of, you've answered a lot of questions already, so I'm not concerned. 1 over, so anytime we take the square root of something, it's going to be 1 over 2 times the square root of that something, whatever.
Some square root of whatever's inside. Okay.
Which is the natural log of arctan x. So everything that wasn't blue goes inside that square root. And we're not done, right? We have to keep going. Now we move into the natural log, and I'll move on to, is it Monado?
Yes,
Monado?
it's Monado.
Okay, I said that right? Okay, good. All right, Monado. So we got to take the derivative of natural log of arctangent of x. So in order to do that, you got to know what the derivative of natural log of something is.
I'm pretty sure it was 1 over ln x.
Close. It's just 1 over x.
1 over x. Just 1 over x. Okay.
Yep. Now for us, is it going to be 1 over x for us?
It's going to be 1 over arctan x.
That's right. 1 over arctan x. Good. Do you want to keep going?
Sure.
Okay. So you've taken care of the natural log part. Now you've gotten yourself down to the arctan x, and you just need the derivative of that.
1 over 1 plus x squared.
Good. And that was the one I asked you to please try and burn into your brain as soon as possible.
Yes.
Okay, there we go. That's kind of like the raw derivative. There's not a whole lot of cleaning up we can do with that. Just kind of, there it is.
I have a question. So what's the derivative of 10 arctan x?
This right here. 1 over 1 plus x squared.
Oh, okay.
Yeah, you know what? It's on that. It's on this side. took it off of here. Here we go. I'll throw it back here just to have it. So we were using that formula right there. That doesn't make sense. I'll put it in yellow. Okay, let's look at the next problem. The next one says, find the equation of the tangent line to sine inverse of x times y squared equals x plus y at the point 0, 0. So again, we're still doing Cal 1 right now. This is, hey, look, we have a curve. We want to find the equation of the line that is tangent to the curve at a specific point. So let's take a look at this curve. What the heck? Let's take a look at this curve. I'm going to go ahead and do it. Open this Desmos and type in arc sine x times y squared equals x plus y. So there's the curve. Okay, there it is. And we want to know what the equation of the line is that is tangent to this curve at the point 0, 0. So at the origin, what is the equation of that line going through that curve? The equation of the line, sorry, tangent to that curve at that point. That's Cal 1 question, isn't it? So let's do it. So what do we need in order to do this? Well, we need the equation of the line, right? The equation of the tangent line. We can use the point slope formula, y minus y1 equals m times x minus x1. Do we have a point on this tangent line?
0, 0.
0, 0. So I know that my equation actually looks like this. Y minus 0 equals m times x minus 0, because this point is the point x1, y1. So that really just turns into y equals mx. So where am I going to get the slope from?
Derivative.
Yeah, the slope is the derivative. This is going to be the derivative of the function at 0, 0. Okay, that's what all Cal 1 was about. We wanted to be able to find the slope of the tangent line, right, at a specific point. So we need to know what y prime is. Well, here's the curve. So how are we going to get y prime? It looks pretty ugly, doesn't it?
A little. Just use implicit differentiation.
Implicit differentiation.
Implicit differentiation. Cameron, were you saying something?
No, yeah, that's what I said. Yeah, I said implicit.
Yeah, so we're going to have to use implicit differentiation. And all implicit differentiation is differentiating both sides of an equation with respect to whatever your variable you want. In this case, I'm going to differentiate with respect to x because I want y prime. So I'm going to take the derivative with respect to x on the left-hand side. And that should be equal to the derivative with respect to x on the right. Did I say right-hand side? Okay, derivative, we're going to take derivative with respect to x on the left-hand side and derivative with respect to x on the right-hand side. I'm going to give you a moment to try and see if you can't work this yourself. Let me give you, I've got to take an important little 1 minute, 2 minute break here. Feel free to talk to one another. See if you can't get the derivative worked out. And I'm just going to warn you, there's chain rule, but there's also some other stuff going on in here. Like right here, right there, there's something. Be careful. And I'll check back with you in just a moment, okay?
How's it going, guys? Y'all want to work together? Y'all all want to just, do this by yourselves?
Yeah, I'm done to work together, but
You have to use the
Just let
chain
you
and the
know, I
product
have like
rule.
2 chickens in my room, so if you hear that noise, that's them.
Chickens?
I got 2 new chickens, and I have to keep them quarantined for 2 weeks, so they're in my room. That would be her.
No way. Oh, okay.
Okay. Oh my goodness. Hang on.
Okay.
The question rule. Kak Iman, oh furanya.
I got dy over dx equals 2y over square root of 1 minus xy squared minus 1. Did someone get something different?
Still working it out.
I'm still working on
it.
Okay.
I've worked it out on the whiteboard here if you want to take a look at it.
Oh, can you simplify the brackets?
Oh yeah, there's a lot that I can do. That's just kind of like the raw derivative, just using the rules at this point. I just want to put it up there for you. So this first part that I did here, this is just the derivative of arc sine, right? That's all that is. Arc sine of something, and it's just whatever the argument of it was, is the part that gets stuffed into the formula. Yes. Is that clear to everyone?
Yes,
Okay.
sir.
Chain rule, then I have to take the derivative of the green part. And that's where I was saying you have to be careful because that's a product rule. Right?
Yeah, that's what I was saying. I was like with the y squared. I was trying to look back at because I have all my notes from Cal 1 here. I forgot what the square was, but it's the 2y prime.
Yeah, so if I'm going to take derivative of that implicitly, I have to use the product rule, which says that you do the derivative of the first one. So this is an important point right now. What is the derivative of x?
1.
1.
What is the derivative of x squared?
2.
No,
2x.
x squared.
2x.
Yeah, I'm going to get a new page here. The derivative of x, everyone in here is in agreement that that's 1. The derivative of x squared, everyone in agreement here that this is 2x. X cubed, the derivative of that is 3x squared.
3x squared.
Okay. Now, the reason why that's true is because when we use that little prime and we say the derivative, we are actually saying to ourselves, the derivative with respect to x of x is 1, right? That's what we're saying, really? Y prime really means derivative with respect to x. But I want you to kind of think of it a different way. We're trying to take the derivative of x with respect to x. That's why it's 1. It's like the same thing over itself, dx dx. When we come here to this problem right here, I'm going to do it to the side. When I say derivative of x with derivative with respect to x of x squared, you're actually doing the chain rule. The 2's coming out times x, right? So the 2 comes out, you subtract 1, you get 1 here. But then you're supposed to multiply that by whatever the derivative of the inside is. What is the derivative of x with respect to x? It's 1, right? And that's why you have 2x. Same thing with this one. Derivative with respect to x of x cubed. You're doing 3 comes out, x squared, but then chain rule says then times the derivative of that base, but the derivative of x with respect to x is 1, and that's why it's just 3x squared. When we try and take the derivative with respect to x of y squared, this is different because the chain rule says the 2 comes out, we get y to the first power, but then I have to take derivative of the base there, the y, the derivative of that y with respect to x, and that's not 1. That's dy dx.
Okay.
And that's where you, sorry, that prime should be a 1 right there. It looked like a, that's a 1.
Prime.
Okay, that looked like a prime. So that's why we get 2y, y prime. So it's very important, right? When someone says take the derivative, like in general, someone says take derivative, you actually really do need to know like what variable you're treating as like the x, right? I mean, it's important that it's with respect to x. You don't always have to differentiate with respect to x. You can differentiate with respect to y or with respect to t, different things, right? Okay, so back to this. That's where this comes from, that product rule. And on the right-hand side, we took the derivative of x, which gave us 1, took derivative of y, which is dy dx or y prime. Okay, now that we have this, all that we have to do now is figure out what y prime is. But we get lucky because we get to plug in, we get to plug in 0 for x and 0 for y into that equation. So let's do that. If we plug in 0 for x and y, what does all this become? If I plug in zeros here and here, get 0 squared, that all goes away. I just get 1 minus nothing, that's just 1, square root of 1. So I just get a 1 here. Do y'all agree?
Get 1.
Yes, sir.
Yeah.
Then times, in parentheses, let's see what all this becomes.
Yeah.
Isn't that 0?
Yep,
Isn't that
0.
Yeah, that's
That's
just 0. So I have 1 times 0 equals, let's see the right-hand side. Right-hand side is 1 plus y prime. So we get 0 equals 1 plus y prime, and that means y prime is -1. So that's the slope of my line. So now I'm ready to kind of come back over here and answer this question. This should be -1 times x. All I did was replace the m with what we just found it to be. Now, if I go back to that graphing utility and I have it graph y equals -x, we should see a tangent line that passes through the origin. There it is. All right. Are we ready for the last problem? We've got about 15 minutes.
Yes,
Tell y'all a quick little story here, just kind of before we get into this word problem. I'll try to make it brief. It's going to take me about 5 minutes to tell the story. So when I was in graduate school, I was in my early 20s. Yeah, early 20s. And in grad school, taking, math courses, I mean, that's all I did. I lived it, breathed it. It was my life, I worked at the university, so I slept in the office a lot of times. I didn't go home to my apartment very often. Sometimes I'd be like wearing the same clothes for like 3 days. It was pretty bad. So I had this rule where like once a month, I would just go out with my friends and just let it all go. You have to have that stress relief, right? So I go out to clubs. I like to go out to clubs and dance because I can just get all the stress out, right? So I had this kind of rule, and I look back on it now and it sounds very stupid and arrogant and dumb, but I was kind of stupid, arrogant, and dumb. So I had this rule that if I ever met like a girl or something, there was like a minimum question that I would ask her to see if we could even like communicate that well, because I was so into math, like she had to have some baseline knowledge of some math, right? Or else I wasn't going to be interesting to her at all. And so I'd always ask the question, what's the derivative of x? Right? I mean, I was like, you know that, and maybe there's a chance that we could talk. I don't know. So this one night I'm out there, I'm dancing, and I'm dancing with this girl for like half an hour. Never talked to her. We're just kind of, you know how that happens on dance floors. You just kind of wind up in front of someone. And so I'm dancing with her, we're having a good time. I go to the bar, she comes up the bar. And I never went up to girls because I knew like I had no time for them. Like it just, I'm not gonna lie to you and make you think that I can actually invest anything into a relationship. So she came up to me and I asked her, what's the derivative of x? And she said to me, her response was, with respect to what variable? And I was like, damn. So I was like, okay, let me follow that up then. Let me follow that up. So the next question I asked her was, if you take the interval 0, 1, all the numbers between 0 and 1, and you just close your eyes and randomly reach in there and grab a number, what's the probability that it's a fraction? Right? So I'm letting you think about that question, but let me say it the way I said it to her. I said, with club music in the background, right? I'm like, what's the probability of picking a rational number out of the interval 0, 1? Okay, that's the way I posed the question. And her answer was 0, which is correct. And I was like, whoa, like that's measure theory. Like, so she knew measure theory. So I'm like, how am I dancing with this person randomly on this night that knows all this? Anyway, we went on to dance the rest of the night. Turned out that she was leaving that next morning. So that's the last time I ever saw her, like in person. But we exchanged emails, and because back then it was like, that's the way you did that, just emails. And I actually, every once in a while, still talk to her. She wound up going on to program robots that weld cars together. So if you've ever seen like assembly lines and the cars come down there and you see all the robots going, welding. So she's like a computer programmer / engineer. Anyway, really, really smart girl. And so the reason I'm sharing that story with you is because I just showed you right here. When you differentiate, when you say, hey, I'm gonna take derivative, what's the derivative of x? Like we all understand, yes, it's 1, but there's a big asterisk there. And the asterisk is that we're making the assumption that you're differentiating with respect to x. And it doesn't have to be with respect to x. And you don't want to get too fixated on that, because if you take the derivative of y squared, I say, what's the derivative of y squared? Well, it's 2y, right? I mean, it could be 2y. When would that be correct? When would the derivative of y squared be just 2y.
When
would
take
that be
it
true?
respect to y.
If you were differentiating with respect to y. So you have to be aware of what the with respect variable is. Otherwise, you're making assumptions. And so if I would just tell you that, it's one thing, but I think the story is kind of cool too, because it kind of helps burn that in a little bit more. Anyway, so don't ever forget, it's with respect to what variable. All right, word problem, 10 minutes. Deep breath. Here we go. Does anyone know what type of problem this is from Cal 1? We call this a certain type problem. We mentioned it when we were talking about the things from Cal 1.
Related rates.
Optimization.
Related rate.
It's a related rate. So we've got this rocket, it's fired straight up, it's traveling 1,000 miles per hour. Some observer who's 1 mile away, it says a mile away from the launch point, is watching the rocket with binoculars. And they're asking at the exact moment that the rocket is 3 miles high, how fast is the observer's angle of inclination changing? And then what is that in degrees per second? So with related rate problems, I teach my Cal 1 classes to kind of try and follow like a sort of template, like try if you can for each problem to do this. I tell them to first draw a general picture. It's just a picture of what's happening. Everything's in motion, nothing is fixed. Then I tell them to try and draw a picture that looks at the instant in time that you're talking about. And then I tell my students to try and write down what they're given and try and write down what they want. So there's kind of like 4 things that I always say on related rate problems to try to do. So I'm going to start with my general picture. And when you see my picture, you're going to be jealous of just the pure talent, okay, in me drawing rockets and stuff, okay? So don't feel bad, I've been doing this for years. So here's my rocket. There it is, okay? It's a big old dot, all right? There's my rocket. It is traveling up, right, at 1,000 miles an hour. There you go. Then I've got an observer, right? My observer is sitting over here on the ground. Again, awesome graphics here. That observer is 1 mile away. And that's not changing, right? The observer's never going to change. They're 1 mile from the launch point. And then I have an angle of inclination. And the angle of inclination is the angle between the ground and the rocket and the observer's line of sight. And I think that's a good enough picture at this point for me to start drawing the picture of like the instant in time. Because if you read the question, it says, at the moment the rocket is 3 miles high. So let me draw that picture. And it's going to look very much the same. Here's my rocket, but now my rocket is fixed. It's actually 3 miles high. My observer's on the ground 1 mile away. This is not drawn to scale. I realize that's not equivalent there. And now my angle of inclination is actually fixed, isn't it? Isn't that theta like actually locked at that instant in time? Now in my general picture, we kind of imagine that everything's moving. But in the instant, it's like someone took a picture, and that's the picture. So could we find theta if I needed to right now? Could you find it? You could.
Yes.
You could actually use the inverse tangent function, inverse tangent of 3/1, because tangent of theta would be opposite over adjacent, so arctangent should get it. Now I'm not going to, but I just want to point out that we could find theta if we wanted to. Now, when we're writing down what we're given, what we really want to try and see is if we have a derivative in here. And we're given the speed of the rocket, aren't we? A speed is a rate of change, and a rate of change is a derivative. So we want to somehow represent that 1,000 miles per hour as a derivative. It's the rate of change of something. right? It's the rate of change of what in my picture? What's changing at 1,000 miles an hour?
The rocket's speed, velocity.
Well, the rocket's speed is 1,000 miles per hour. But what is changing?
The angle of
rocket's height?
inclination.
The height.
angle.
Okay, so the angle does change as a result of the altitude of the rocket, right? But the 1,000 miles per hour is how fast that distance is increasing, right? Straight up. So that means on my general picture, I'm going to come in here and add a variable right in here. I'm going to call the distance from the ground to the rocket, I'm going to call that h, just for height. And if I call that h, then I can come back over here and I can say that the 1,000 miles per hour is the change in h over time. Okay, what is it that we want? So let's go back over here. At the moment, the rocket is 3 miles high. How fast, speed, derivative, how fast is the observer's angle of inclination? So we want to know the rate at which the angle is changing. How can I represent that in terms of like mathematical notation?
D theta over dt.
D theta dt, good. D theta dt is what I want. Put a question mark next to it. I want to know how fast the angle is changing. I don't want to know what the angle is. That's not a calculus question. I want to know how fast that angle is changing. And I want to know that at the exact moment what?
When it's 3 miles in the air.
That it's 3 miles in the air. But I don't know if you said, James, h, but I'm going to put here at h equals 3.
3.
Because we actually have a value, and we've now assigned a variable to that height. Okay, recap, general picture, everything's moving, everything is a variable. Instant picture, things are locked. Write down what we're given, try and get derivatives in there if you can. Write down what you want, try and get derivatives. And now the next step is you need an equation. You need any equation that's out there in the world of equations that somehow is going to tie the variable h to the variable theta. You have to tie those two variables together within an equation. And you have to look at this picture.
Can we do speed over distance, speed equals distance over time?
Yes, that would be true, but we're trying to find an equation that will somehow link the h variable in our picture to our theta variable. So look at this picture over here. I'm going to kind of erase a couple of things in here. This is h, isn't it? So look at that right triangle. This is h, this is 1, and this is theta. Is there any way you can put those together in some connected formula?
Tangent
theta equals h over 1.
We know tangent of theta equals h, right? That we know is true. And now that we have an equation connecting them, we're going to come in and we're going to differentiate it. We're going to differentiate it with respect to
theta.
What is our given information? With
h. Time.
Time,
E
right?
over dt.
We're going to take the derivative on both sides with respect to time. Now, the reason we're doing this is because when we do it, we should get d theta dt should pop out, and so should dh dt. Let's do it. So I'm running out of time, so I have to go faster. The derivative of tangent theta is secant squared theta times chain rule, the derivative of the argument. What's the derivative of theta?
D theta over dt.
D theta dt. So again, this is where we have to be careful, right? The derivative of theta is not 1 because we're differentiating with respect to t. So it's d theta dt. Now equals, now on the right-hand side, what's the derivative of h with respect to t?
dh over dt.
dh dt.
dh dt. And dh dt is 1,000 miles per hour.
Yes, exactly. So now look, we're very happy now. Here's why we're happy. dh dt, we know its value, right?
Yes.
D theta dt, is what we're looking
Is
for.
what we need.
And the only thing we don't know at this point is theta, but we already said earlier we could find it, couldn't we?
Yeah.
So we're like, check, we know what that is, like, check, we know what theta is, and you know what, this is what we wanted to know anyway, so we should be able to solve that equation. We'll have it, right? Everything good?
Uh-huh.
Okay, I've got 1 minute, because I'm gonna redo the problem just real quick over here on the side. When we were at this stage right here, when we took the derivative, we're right here at tangent theta equals h. Watch what I'm gonna do. Before I differentiate, I'm gonna take arc tangent on both sides. Okay, my left side becomes theta because of the cancellation property. My right side is arc tangent h. Now I'm going to differentiate with respect to time. So what would be the derivative of theta with respect to time? So I'm doing derivative with respect to time here.
d theta over dt, and then
Yep, I'll have d theta dt equals, now what's the derivative of inverse tangent of h?
1 over 1 plus x squared.
1 over 1 plus h squared. Now chain rule, be careful. Now you have to take derivative of h. Right, you've got to go inside the trig function, take derivative of h, which would be
dh dt.
Okay, and we'd be done. I mean, at least with the derivative. Now check this out. D theta dt is what I want to know, right?
Yeah.
And dh dt, I have. But I also have h, don't I? I know h is 3. So look, both of these ways will get you to the same answer. They both give you the same answer. But do you see that the way on the right, we never have to solve for theta? Like we never ever need theta. We just need h in dh dt. So I would argue that this way is more efficient, right? It's a little more efficient, but it used the inverse trig function, which before today, we did not know what the derivative of that was. So we couldn't have done that way on the right before today. Now we can. Okay, that's all we have time for. You should be able to do your homework at a 3.5 now. And we'll come back next week on Tuesday and we'll hit it pretty hard. All right, we're going to start grinding. We're going to start to get the train moving. All right.
Sir, how fast is the recording going to be uploaded? Because I got here a little bit late, and I just want to make sure all my notes are done.
Yeah, this should be. I started, I think, like the recording like 2 minutes into class, so it's a little bit behind. But yeah, I'll get up. It may not be till later on this afternoon because it usually takes the system like an hour or two to get it to me, and then I've got to upload it, and I'm not going to be here. I've got to run for a little while, so it'll be later this evening.
Okay, sir. Thank you.
Mm-hmm. Did someone else have something?
Where in on Canvas, like, will you upload the videos to? Like, will it be under files or?
No. Let me just take you there real quick.
All right, this one.
I want to make sure they're there. So this is it, right? This is the class, section 9. So if you this is the main home page. So if you come down to class lecture videos, click on that. There they are.
Okay.
So I have the introduction, and then this was the class from Tuesday.
Yes, sir.
Okay. And if you want, you can also save this playlist if you want. What's that?
So you're going to be uploading all of these to YouTube?
Yep.
Okay.
Yep. And remember, I also already have like hundreds of videos from past semesters too, you know? So like if you ever wanted to just get ahead or go back and look at something, because sometimes I present things in different ways, so.
Where can we find the homework uploaded videos? Can you show me that again?
Yeah. So back here, we had the class lecture videos, right?
Uh-huh.
And then right below it is the homework solution videos. So that's me working through all the homework problems. All right. Okay. I think we're done.
Thank you, sir.
Yep. Y'all have a great weekend. See you on
Thank
Tuesday.
you.
Thank you.
Take care. Good weekend.
Yep.
Have a good day.
Okay. Bye-bye.
Bye-bye.
I need to stop recording.